Thank you very much, Phil. It's a real pleasure to be here, especially seeing all those students and faculty here. That's a special treat for me. If you get nothing else this afternoon except some lunch, that's not too bad. So, there's this old theorem 208 that says if you feed them, they'll come, and here you are. So that must be true. I'm sure you aren't here just to hear me because, a meal is probably more important. And if you decide this is all very boring, at least you went away with a full stomach. So, a couple of things. I have a bunch of slides here, and the most important point that I want to make before I even put more slides up than that first one is the Internet is not done yet. The design started in January or February or so of 1973, almost 40 years ago. And in spite of the fact that it has evolved over this period of time, the fundamental architecture is very, very much as Bob Kahn and I envisioned it to be. But the point I want to make is that it isn't done yet, and there is more to be done. The architecture can, should, and probably will evolve, and you're going to be involved in some of that. So I want you to go away today realizing that you still have an opportunity to do things to make the Internet different and probably better than it is now. So this is not a done deal. It's not over. It's just the beginning. So let me go back in history just for a second. In 1969, it was not thought that packet switching was a smart idea. In fact, the telcos of the world at that time, and mostly AT&T, thought that this idea of packet switching was crazy. Now, you all understand that's how the Internet works. It's breaking information up into little chunks with source and destination addresses on them like little postcards, and they go routing through this very store and forward network, very much like the post office, but about 100 million times faster. It was thought, that was a crazy way to have things communicate with each other. After all, the way humans talk was to dial up a number, get a circuit, have the circuit was dedicated to your use until somebody hung up. Even if you weren't talking, the capacity was still dedicated. The packet switching world allows the same capacity to be used over and over again. As soon as you got rid of one of these little electronic postcards, the next one could go on the channel. So it was this mixing and sharing that allowed for very efficient use, very rapid exchange of information. So there was a project started by the Defense Department, specifically the Defense Advanced Research Projects Agency, called the ARPANET. And that project was to see whether or not computer communication using this packet switching idea would work. We started with a 4-node network, and I was a graduate student at UCLA in 1969 when the first node was installed in September. I wrote the software for this little machine called the Sigma 7 in the lower right-hand corner to connect it to the first node of the ARPANET at UCLA. Well, the Sigma 7's in a museum somewhere now, and some people think I should be there too, but here I am. This was the beginning of an experiment to see whether this technology would be good for computer communication. We fast forward about 30 years. Lots of things happened in between, one of which was the design and implementation of the Internet, which evolved out of these early experiments. This picture is important for a couple of reasons. First of all, it was automatically generated by looking at the routing tables, the global routing tables of the global Internet. Those routing tables tell each one of the routers of the network what to do with one of these electronic postcards that shows up, because you look at the packet and you say, where is it supposed to go? Then you look in the routing table and it says, if it's going to that place, then send it out this channel. Send it to this other router next to you over this channel. This is a multicolored picture because there are many, many networks in the Internet, hundreds of thousands of them, millions of them if we include the little network you probably have at home. You have a dedicated link of some kind, and you probably have a Wi-Fi server as well. And so you're part of this colored picture. The thing that's important about the picture is that those hundreds of thousands of networks are operated by different entities. Some of them are for-profit, some are not-for-profit, some are government. They are all interconnected voluntarily. Nobody forces them to connect. No one forces them to build pieces of Internet. No one forces them to invest in upgrades and expansion. It is completely collaborative, and it is global in scope. There's no central control in the system, and it was designed that way on purpose. When Bob and I were first thinking about this, we wanted to have a global system that could grow organically. So we released the specifications for the Internet publicly. The first paper was issued in May of 1974. with no constraints, no patents, nothing. We just wanted people to know how to do this, and then we said, if you can build a piece and find somebody to connect to, this network would grow in a very organic way. Guess what? That's exactly what's happened. So today you see a network in 2012, which is just like this, only bigger and more colorful. In terms of size and scale, there are about 900 million machines that are on the network that have domain names that are fixed and IP addresses, Internet Protocol addresses. Those are the numeric equivalent of domain names. Those 900 million machines are typically the servers that you go to for World Wide Web service or for email or streaming video and things like that. There are a lot of machines that you can't see publicly. There are companies, Gallup is a good example, my company Google is another one, that has a large number of machines that are not visible directly because they're hiding behind firewalls. So their absolute number of machines and servers on the net is vastly bigger than 900 million. These are just the ones we can see visibly. On top of that, there are things that are connected to the net episodically, like your laptops, desktops, and mobiles, and things like that that are not always on necessarily. And so there's an even larger number of machines than the ones that are physically connected all the time. And that simply adds to the need for larger and larger address space on the net. In terms of where the people are, there are an estimated 2.3 billion people online right now. That's out of the 7 billion people on the planet. And so as the chief internet evangelist at Google, I have several billion people more to convert. So I can use help. You know, if you're interested, please let me know. This is still an evolving process. And again, it's another reason why the internet is still in evolution. These are where the users are. And this is an important thing for anybody who is thinking about doing business globally using the internet, because you have to understand the nature of the online markets. Asia has over 1 billion users online, and half of them are in mainland China. 500 million people are online in China. Despite all the bad things you may hear about Chinese hackers and attacks and suppression of free speech and everything else, the Chinese are still investing heavily in building infrastructure to support an increasingly large collection of users in country. So they recognize the importance of the technology, even though they are also concerned, obviously, about what its potential side effects are. Europe has 500 million users, but I no longer make any predictions about Europe because they keep adding countries. So the definition of Europe keeps changing, so I've given up making any projections there. The rest of the numbers are as you see them. Africa is a big challenge, although recently, one of the things which has become very apparent is that the 140 million online shown in this chart is an undercount because there are a large number of people in Africa with mobile phones that are internet enabled. And so these statistics tend not to include people who are exclusively on the net using mobiles. This brings another point to the table, which is that mobiles have turned out to be incredibly important. They are devices that are programmable. They're not just telephones. But their power comes not simply because they're programmable, but because they're able to interact with and exercise the horsepower that's on the internet. And so it's this connection between a mobile and the internet resources that have made both of them so important and so valuable. Because now I can, from anywhere that I can get mobile connectivity, I can typically exercise an operation on the internet. So when you send a tweet, for example, you send one message through the mobile system to a host on the internet, and it replicates that tweet 100,000 times or 100 million times. So this is the synergy between the two that's so powerful. And it's a huge opportunity for people who are interested in building new applications, because they can build them on the mobile side and then exercise facilities on the internet. Now, I have a bunch of slides that relate to the design and architecture of the internet, and I realize I have a short amount of time and I don't want to turn this into a terribly dry lecture, but I do want to just pick a few points about the way it was designed, again to reinforce for you that this design is still extensible and still has a lot of room to grow. New ideas are welcome. So when we started out, Bob Kahn, who started the project, there are two of us who began, but I was invited to participate by Bob Kahn, who at that point was at the Advanced Research Projects Agency, thinking about open networking. How do I build different kinds of packet switch nets and get them to interconnect, which is why we call this the internet. His notion was that we use different kinds of communications technologies to build networks. It could be mobile radio, it could be satellite-based, it could be wireline, coaxial cable, and at that time we didn't even have optical fiber, except maybe in laboratories. We knew that we were going to have a variety of new communications capabilities evolving over time, and we wanted the Internet to be capable of absorbing any new technology that came along. So we designed it in a very layered way. And sometimes you'll hear the term layering in association with the Internet's architecture. The lowest layer is physical layer, where bits get moved on fiber or on coaxial cable or on a satellite link or a mobile radio link. The Internet packets that are carried by this physical facility have no clue about how they're being carried. Just like a postcard doesn't know that it's in a postman's bag or in a postal vehicle or an airplane or a train or a truck or something else. It just doesn't know. And the postcard doesn't care, just like the Internet packets don't care. All they care about is that the bits get moved from point A to point B with some probability greater than 0. So the design to make these Internet packets ignorant of how they were being transported meant every time a new transportation communications capability was invented, we could sweep it into the Internet architecture. So when the mobiles of today came along, we could sweep those into the architecture. When optical fiber came along, that just became another bearing channel. So the Internet packets, their ignorance of how they were being carried was a virtue. In fact, if you want to be extreme about this, the Internet was not designed to do anything in particular. Unlike the television broadcasting system or the telephone system, which were designed to do a specific operation, we did not design the Internet to do anything in particular. We just designed it to move packets around. And this gives it its great flexibility. The other piece of ignorance that turns out to be important is that the packets don't know what they're carrying. Just like a postcard doesn't know what's written on it, an Internet packet has no idea what the bits mean. It just knows there's a bag of bits. And the result of that design choice is that the only place that cares what those bits mean are the computers at the edges of the net, whether it's a mobile on one end and the supercomputer on the other, or two supercomputers talking to each other. Those computers are the only ones that know what the bits mean. So if you want to invent a new application, you don't have to change the Internet. You just have to change the interpretation of the bits that are carried around in the packets. That's why people have been able to invent new applications on the Internet without having to run around getting permission from every Internet service provider in the world or changing the underlying Internet. It is ignorant. In fact, there was a wonderful paper called The Rise of the Stupid Network, because it didn't know what it was carrying. So the result is companies like Google get started by Sergey Brin and Larry Page. They didn't have to run around asking permission to set up the service. They just put it up and let people get access to it. And of course now, 14 years later, we have a very powerful company with 50,000 people and all continuing to grow new applications day by day. The other thing that was kind of interesting is that the networks of the time, and there were networks. IBM made its network called SNA. Digital made a network called DECnet. Hewlett-Packard made networks called DS for distributed systems. Each network thought it was the only network in the universe. There was no way for a computer on one of these proprietary networks to say, I want to send a message to a machine on another network that's of a different type. So we had to invent a global addressing scheme that would allow anyone on any one net to say, please send this to another machine on another network somewhere else. That's what the Internet addressing was all about. And we'll discover later a mistake that we made, but I'll tell you how we got there. We started out thinking, okay, we've just built this ARPANET thing. We built a packet radio net and a packet satellite net. These were not inexpensive things to do. So then we said, all right, we're building this global Internet. How many networks will there be in each country? And we thought, well, they're pretty expensive, so maybe there'll be 2. And then we said, how many countries are there? And we didn't know, and there wasn't any Google to go to find out. So we, we're computer programmers, so we always think in powers of 2 anyway. So we said, well, there's probably about 128 countries, so that means 256, which means 8 bits. So we'll use 8 bits for the country identifier, and then the other 24 bits are for computers. And at the time, we thought 16 million computers per network was more than enough, because at the time, The computers were big, huge machines costing millions of dollars, and they were in air-conditioned rooms, and they didn't get up and move around. So we started out with this 32-bit address space. That was enough for 4.3 billion terminations if you do, 2 to the 32nd. And we thought that should be more than enough for an experiment. And I thought, when I was running the program for the Defense Department, that if the experiment worked, then we would design a production version of the system. And what happened is that the experiment never ended. So you are using the experimental 1978 standard internet today. And last year we ran out of the what is called IP version 4 address space, and I'll come back to that. So I've already talked about some of these things. Let's see if there's anything else. Oh, there's another interesting thing about the IP address structure. In the telephone world, it was common to have a country code on the front of the telephone number, and so every country had its own telephone address space, telephone number space. I didn't want to do that for the Defense Department, and I think it should be obvious when I give you the scenario. I was thinking, okay, if we had had country codes as part of our addressing structure, imagine you're country X, and you're planning to attack country Y in 2 weeks, and you realize that you're going to have communications infrastructure in place in order to carry out command and control. So if everything was country coded, you'd have to go to country Y and say, excuse me, we're planning to attack you in 2 weeks, and we need to have some address space in order to set up our command and control system so we can successfully overcome. And of course, that doesn't work. So we said, okay, no country codes at the address space level. Everything is related to connectivity and topology. So the addressing space of the internet is associated with networks and how they're connected, and not with their geophysical location. Ironically enough, when we get to the domain name system, people that's visible. Domain names are visible to people, whereas internet addresses are not. And then they wanted visibility of country codes. They wanted to be able to say, hi, I am operating in Germany.de, or I'm in France.fr, or I'm in the US.us. And so the domain name system actually has geographical indications, while the address space does not. And companies like Google and others discovered utility in mapping the address space, the numerical address space, to locations. So that if somebody said, hello, I'm coming to do a Google search, if you could figure out that the address was in France, you would produce the Google page in French. And so there were a number of reasons why my basic idea, motivated by Defense Department needs, has been distorted by the commercialization of the internet, but that's what happens sometimes. I mentioned openness indirectly. That is to say, the packets don't know what they're carrying. The packets don't know how they're being carried. The specifications for the internet were not constrained or by patent or anything else. The process by which internet has evolved is incredibly open. There's this group called the Internet Engineering Task Force. They're operated under the auspices of the Internet Society, and you can't join it. You can just show up. That's all you can do. There's no way, there's no membership. You can't be booted off. You just show up. And if your ideas are accepted to other people, they'll be adopted. And if they aren't accepted by other people, they won't. It's an entirely meritocracy. And it's so open and very global that lots and lots of people have been able to bring their ideas to the internet and get them adopted as part of the evolving standards of the system. So this openness stemmed from one interesting fact. The internet was not designed by the telecommunications business, nor was it designed by telecommunications engineers. It was designed by computer scientists, and they were in the academic world. Now, in the academic world, we don't buy information from each other. Our medium of exchange is information. I will give you some information if you give me some. And so this open sharing of knowledge and information is what drove the internet's architecture and design. It is what drives the standards making of the internet today. And that is a really important thing to hang on to, because ideas come from everywhere. We don't have a corner on creativity in the United States. We have lots of smart people here, and there are lots of smart people out there, probably more smart people in aggregate, because we only have 330 million people in the U.S., and there are 7 billion people on the planet. So there's a lot of smart people out there. We want their ideas to show up as part of our world as well, to take advantage of that, and that's what the internet has done. There are some huge changes going on in the internet today, and again, this is a reason why you have opportunities to participate in and to affect the way in which the internet evolves. We ran out of the version 4 address space in February of 2011, and we introduced in June of this year, we being the community that implements and operates the internet, a new IP version 6 protocol that has 128 bits of address space. 2 to the 128th is 3.4 times 10 to the 38th. That's a number only the Congress can appreciate, but it's a big number. It's 340 trillion addresses, which ought to be enough to last until after I'm dead, and then it's somebody else's problem. So we now have this huge address space available to us. It's not implemented everywhere, but it is implemented increasingly widely. It's in the routers already. It's in the end devices already. If you have a Mac or a PC or something, they already have V6 as well as V4 format capability. The internet service providers are the ones that have been slow to turn these things on. So if I were in your shoes looking at broadband services, the first question I would ask, in addition to what are the prices and what are the speeds, is also, do you implement IPv6? And if the answer is no, the response should be get with it because you're going to need it. We've also added, we in this case the Internet Corporation for Assigned Names and Numbers, which is responsible for the domain name system, has opened up the top-level domain space, which used to be things like .net, .com, .org, .edu, and country codes like .de and .fr and so on. They've invited proposals for new top-level domains. 2,000 proposals came in. They haven't been implemented yet, and they're still in the process of evaluating. Some companies propose the same top-level domain, so they have to sort out the collisions. But it is going to change the face of the domain name system to have many, many new top-level domains available. The other thing which is very important is that for many years, the domain name space was always written in Latin characters, just the letters A through Z, the numbers 0 through 9, and the hyphen. But it's pretty clear that as the net grew and penetrated globally, that there were a lot of places in the world whose languages were not expressible using Latin characters. So in 2003, we began in the Internet Engineering Task Force and finished in 2008 the design of a domain name system that would allow other non-Latin characters to be used as part of the domain name space. So now we can accommodate Cyrillic and Arabic and Hebrew and Urdu and many, many other languages whose character sets are expressed in what's called Unicode, which is an encoding scheme that has at least 100,000 different characters in it for many, many different languages. There are some other things in here having to do with security, and in the interest of time, I'm not going to go into detail, except to say that the internet is not as secure as we would like. It's not as safe as we would like. It needs to evolve. We need to install and retrofit security mechanisms into the domain name system, in the routing system, into the end-to-end communication system, into your email, into your web services. All of those need to be improved, and the technology is available now to do that. Whereas in 1973, the technology that was available to do it was classified. I know because I was working with NSA then on the design of a secured internet, but I couldn't tell any of my colleagues who didn't have clearances. So we could not release the secure design until now. We have technology that's available to the public key crypto in particular, that can be used to secure more of the net, and that is going on as we speak. The other thing which is very important and which drives the need for larger address space is the number of devices that are being connected to the net. The sensor networks are starting to show up. Smart devices in the smart grid program, appliances around the house, and things like that are all becoming part of the network environment, as are, of course, the mobiles. Here's some pictures. I know you probably can't see these too well, but these are top-level domains written in character sets other than Latin. And so those are quite real. Many of them are already operating. There's one here on the screen that instead of being something that you recognize as characters in another language is just a little set of square boxes, it's because my Macintosh at the time didn't happen to have the Sinhala character set that put that up. So the point here is that as we see more and more of these new internationalized domain names, you may actually see some funny little square boxes because your computer doesn't have all that it needs to render these new language character sets. Now, I mentioned security problems. There are a bunch of them, and some of them, spam, for example, have been just a terrible waste of bandwidth. That is actually starting to diminish, believe it or not, and the reason is that the spammers are not getting the result that they used to get. They would send out hundreds of millions of messages, and a few stupid people would click on them. And now, it's turning out people are getting smarter about not clicking on spam or recognizing spam or filtering spam. At Google, our Gmail system is pretty good about filtering spam out, so you never see it, even though it's present. So now they're going after what's called spear phishing, which is sending emails that look like they are from somebody you know or somebody you should know, with a title and a subject that sounds like you really should look. You open up the message, and there's a virus waiting for you, or there's some other thing that will infect your machine. So spear phishing is becoming a more popular way of invading the system. We have a lot of technical problems associated with security. The browsers are one of the primary avenues through which machines get infected. So if you're looking for some interesting challenges to think through, take some of the open source browsers like Chrome and consider analyzing how it could become more and more effective at detecting and shielding users from the presence of viruses on incoming web pages. Remember how these browsers work. You say go to www.something.com, and your machine goes out and downloads the home page of that website. It just copies a file into your machine, and that's now interpreted by the browser. In the early days, when Tim Berners-Lee first released the World Wide Web, about all those files had in them was text and images and some formatting information. That was pretty innocuous. But in 2012, what those files have is JavaScript and Java and Python and other high-level languages, which are interpreted by the browser. And if the browser is not smart about it, what it's interpreting is code that stores viruses and worms into your operating system. So you have to become almost paranoid about writing software that's defensive to protect you against some of these problems. There's also a set of things that are not so technical in nature. For example, people create their own security problems by picking really bad passwords. And reusable passwords are absolutely the worst. Some people still use the word password as their password because it's easy to remember, right? And the problem is a lot of other people know that, and of course they break into your machine. So we're big fans at Google of what's called two-factor authentication, which means not only do you have a username and a password, but you also have something, a device, which generates in my case, it generates a 6-digit random number. And every 30 seconds, that random number changes. So the result is that even if somebody sees that number going into my system when I'm logging in, they can't reuse it because it's been changed 30 seconds later. This notion of two-factor authentication, something you know and something you have, is powerful, important, and available to the public. So this is an example of things that we need to do to change the way in which we use the net. The last bullet here reads spectacular human error, and the only reason I bring it up is that that's another major security problem. People just mess up. They do configurations that are wrong, and they don't know that until it's too late. Figuring out that a configuration has a vulnerability is actually quite hard. And so if you're looking for another dissertation topic, figuring out whether a configuration of a router or configuration of a computer opens up a vulnerability is a really hard, interesting, and tough research problem. But if anybody figures it out, they will be lauded as heroes. There are a lot of reasons why we have these weaknesses, but the most important of them, I think, is the naivete and bugs in the operating systems and the browsers that we use every day. There are some other problems, and these I want to dwell on for a moment because I think it's important to recognize that some of the privacy problems we have are not evil companies that are trying to steal away some personal information and abuse it. It's things that we do without recognizing that they have privacy impact. So let me see if I can make an example. Phil, you've gone to Egypt, and you're standing in front of the pyramids, and you would like to have a photograph taken of you. So it's Adam over here. Adam, whom you don't know, takes a picture of you. And Paul is sitting next to you, or standing next to you. You don't know him from Adam, and you don't really care, but I didn't mean that, Adam, but you know what I mean. Sorry about that. But it's true. You don't know him from Adam. So anyway, Adam takes a picture. Adam takes a picture of the two of them, and then Phil gets his camera back, uploads it to Google Plus or Facebook or something else. And then somebody else comes along looking for pictures of pyramids, and they see this, but they also happen to know Paul. And so they tag this as Paul Allen. Someone else is going around looking for Paul Allen, probably the other one, but anyway, they find Paul's picture annotated, tagged on the net because of what was uploaded by Phil. And it shows that Paul Allen was in Egypt on June 27th, 2012. Except that Paul told the person who was looking at this that he was in London at the time. So now the picture that Phil asked Adam to take, that he innocently put up on the net, that somebody else tagged with Paul Allen's name on it, has Paul Allen in trouble with somebody else. And it wasn't anybody's immediate intent that Paul Allen be in trouble. It's just that this sequence of events, which looked like it was innocent on the surface, had a personal side effect. The reason I go to all this trouble is that I think there are a lot of things that happen in the net environment now that we don't recognize as being potentially harmful to people's privacy. The devices we're carrying around can record video, can record still images, can record sound, have the ability to upload into the internet, and the internet has the ability to make things widely available on a global scale. So we are going to have to evolve what I would call social practices and social conventions to protect our privacy. I don't even know what those rules should be right now. I think we're going to have to live through some of the things that are harmful in order to figure out what the right convention should be. But I'm sure they will eventually come. I mean, it's like walking, when you're walking down the street and there's somebody coming the other way, usually we just get out of each other's way. I mean, we don't just stand there facing each other waiting for the other person to move, unless we're, particularly a chip on our shoulder or something. And so these are social conventions that make life a little nicer. We have to evolve social conventions for the internet environment that we haven't yet figured out yet. I'm going to skip over cloud collaboration in the interest of getting to a point where we can do some Q&A, except to emphasize for you that clouds have become extremely important because they're so flexible. They give enormous amounts of computing power dynamically allocated to the need of a user. And as soon as that need is satisfied, the capacity goes to somebody else. So it's not dedicated. It's very dynamic. There's huge amounts of storage that are available in clouds. But if you're interested in doing something as powerful as the internet has been, now is a good time. Because there are lots of different cloud systems. They're not the same. They're not identical. They don't interact and interwork with each other. People remotely access clouds and run programs on them, but they don't move data back and forth between clouds automatically. They have to download the data from the cloud and upload it to the other cloud themselves. If clouds could interact the way networks interact in the internet, we would have an incredibly powerful range of tools available because we could move large amounts of data from one cloud to another to take advantage of special processing capabilities or other kinds of features that one cloud might offer. Intercloud is the new internet, except it's at about the same state of immaturity that the network world was in 1973. So if you're looking to do something that has a big impact 40 years from now, now's the time to start studying how to get clouds to interact and what standards we should use for the representation of data, for the control of processes that are running and interacting with each other in multiple clouds. Now, I have a set of slides that talk about internet research problems, and they are sufficiently esoteric and boring that I'm just going to step through them, and I won't expect you to react much, except I'm going to mention one thing. Here's a problem over here in broadcast utilization, the far right here. In a sense, it's related to the broadband topic of interest to this group. I want you to think for just a second what we do with radio. Most of the time, we take radio and we use it to form point-to-point connections. We even take broadcast radio and turn it into point-to-point connections. That's how Ethernet, or I'm sorry, how Wi-Fi tends to work. We take this broadcast Wi-Fi capability, but we end up fashioning point-to-point connections out of it. The reason that that's unfortunate is that there are times when you want the same information to go to a large number of people. And the fastest and most efficient way to do that is to broadcast the information. So this is missing from the Internet Protocol suite, is handling of the use of real broadcasts to replicate data to a large number of receivers. What I'd love to see is satellites in synchronous orbit dropping packets down to hundreds of millions of receivers at the same time for that information that they all are interested in, or most of them are interested in. And if you want to control who can use it, you can encrypt it and give keys only to the people who should get the information they want. But it's incredibly efficient. We don't do that. And there are a whole bunch of other functionalities that we could do and don't do, including multi-homing, where you're connected to multiple networks at the same time. All of these will admit of new protocol designs. And so this is another reason why the Internet isn't done yet, because there are all these opportunities to invent new ways of utilizing communications capabilities. This is another slide. Again, here's an example of a really tough challenge. Multi-core processors. Moore's law used to be expressed as the clock speed going up by a factor of 2 every 18 months, which meant you could be a really crappy programmer and your software would run better every 18 months by a factor of 2. And so a lot of programmers got pretty lazy. You know, they'd write the software and it was pretty crappy, and then 2 years later it seemed to get a lot better, and you hadn't done a thing except the clock speed had gone up by a factor of 2. Well, the clock speeds are not going up anymore, and the reason is that the faster the clock, the more power you consume, and the more power you consume, the more heat you generate, and eventually the chip melts. So, you know, melting chips is not a really good business model. So instead, in order to keep the number of cycles going up, the chip makers put multiple computers on each chip, multiple cores on each chip. And so with time now, we will see 32 processors on a chip or 64 processors on a chip. The problem now is, how do you keep all those processors busy? Now, in order to keep 64 processors busy on a chip, you have to push a lot of data in, pull a lot of data out. And the real estate on the chip that lets you move data in and out of the chip is not getting any bigger. So there's a little bottleneck right there trying to use multiple cores, on top of which writing software to run in parallel on multiple computers is also not a trivial exercise. You get into all kinds of interesting timing problems where two things are going on at once, and then there's a collision. And the software that we were thinking of was very serial, but it was running in parallel, so we have conflicts. Those are all really hard problems to solve, and they involve new language designs, new kinds of compilers, and other kinds of things, to say nothing of chip designs in order to increase I/O. This is one of among many different things that are part of the space of research to be done. Mobile operation is also a very interesting thing, because we keep making and breaking connections. It's not necessarily a solid link in the same way that coaxial cable would be. And the protocols of the Internet are a little brittle when it comes to connection and disconnection. So once again, there's an opportunity for improving the resilience of the system by changing the protocols to be a lot more resilient. I'm going to skip over this slide now. Another thing that I just want to draw your attention to is that although I'm an engineer by trade, some of the hardest problems that I have encountered over the last 4 decades have not been engineering problems, they've been policy problems. And the reason that they are so hard is that engineering is about making measurements, making models of things, and trying to calculate the best option for design. Policy is about opinion and emotion and feelings. This is much harder to come to resolution for. And if you're going to get into serious networking involvement, you will eventually run into policy problems in addition to the technical ones, and they are by far the hardest to deal with, particularly when it's a global environment, because now you have issues that cross national boundaries. You have cultural variations that change people's opinions about how things should work or what policy should be adopted. There are an enormous number of those today, and because the Internet is so penetrant, and because it is so open, and because people are enabled to speak their minds, there are countries in the world that don't like that, are fearful of freedom of expression, and will do anything they can to suppress that. And so now we're seeing actions taken on the international stage by countries like Russia and China and Saudi Arabia and Brazil, believe it or not, and South Africa and others, to do everything they can to make it internationally acceptable to censor the Internet and to prevent people from communicating with each other. This is a huge policy issue. It's coming to a head in December of this year in Dubai, when the international telecommunications regulations are reopened since 1988 to be revised, and we are seeing countries trying to inject into those international telecommunications regulations making legitimate these various censoring activities, among other things. So this is a big deal now. It's going to be a continuing problem as the internet spreads. So I'm going to flip over here to the device and the Internet of Things world. For me, anyway, maybe for you this is not too weird, but for me, having somebody come up and say, look, there's a picture frame on the internet, it's sort of a what? Why would anybody put a picture frame on the internet? Well, the answer is it can download images from websites and cycle through them, so people with digital cameras can upload things and let other people see what they're doing. There are telephones that look like telephones, but they're voice over IP boxes. There are refrigerators that are on the internet. There are high-end refrigerators with nice touch-sensitive displays that you can put in the kitchen. I used to wonder, what do you do with an internet-enabled refrigerator? And of course, you can put up, messages. The family can exchange websites and tweets and other things. But I thought it would be more fun if the refrigerator had an RFID chip on everything that's in the refrigerator, so it knows what it has inside. So while you're at work or at school, it's searching the net for recipes that it could make with what it has inside. So when you come home, you see a list of recipes that it can make. And, that sounded like kind of a cool thing. But the Japanese have messed it up with an internet-enabled bathroom scale. And so now, you get on the bathroom scale and it figures out which family member you are and it sends the data to the doctor to be part of the medical record. But the refrigerator's on the same network. And so when you come home, you see diet recipes coming up. Or maybe it just refuses to open, which is, it's a terrible thing. There's another guy in the Netherlands who has an internet-enabled surfboard. I have an image of him sitting on the water waiting for the next wave thinking, if I had a laptop in my surfboard, I could be surfing the internet while I'm waiting for the next wave. So he put a laptop in the surfboard and put a Wi-Fi server in the rescue shack, and now he's selling this as a product. Now, I used to tell jokes about internet-enabled light bulbs, and someday every light bulb will have an IPv6 address in it. Well, I can't tell jokes anymore. Somebody sent me an internet-enabled light bulb with an IPv6 radio in it, so you can remotely control the light bulb or sense its state. Now, I mentioned earlier sensor networks becoming a part of the internet, and I believe this is very much going to happen. Buildings will be fully instrumented for security, for environmental control, management of the heating, ventilation, air conditioning, all these other things, lighting, and so on. I have an IPv6 radio network at home. This is a commercial product. I didn't do this with a soldering gun in the garage. It's by a company named Archrock. Every 5 minutes, these little battery-powered devices sample the temperature, humidity, and light levels in each room, and they report that back to a server that's down in the basement. So at the end of the year, I have good engineering data about how the heating, ventilation, and air conditioning system worked, so we can adjust the fan speeds and the baffles and other sorts of things to more smoothly heat and cool the house. One of the rooms is the wine cellar, and it needs to be kept below 60 degrees Fahrenheit and above 40 degrees or 40% humidity. So that one's been alarmed. So if the temperature goes up above 60 degrees, I actually get an SMS on my mobile to tell me that there's something wrong with the wine cellar. This actually happened not too long ago. I got a note saying your wine is warming up. And I wasn't at home at the time to go reset the cooling system, and my wife was away too. So for several days, the wine kept warming up, and I kept getting a message every 5 minutes saying your wine is getting hotter. So I finally got home, and I called up the Archrock guys, and I said, "Do you make a remote actuator?" And they said yes. I said, "Do you have strong authentication, two-factor authentication for it? Because I have a 15-year-old next door, and I don't want him messing around with my wine cellar." They said yes. So that was a weekend project. Then I got to thinking, I could actually tell if somebody's gone into the wine cellar when I'm not there because I can see the lights go off and on. But I don't know what they did in there. So I thought, why don't I put an RFID chip on each bottle? And then I can do an instantaneous inventory of the wine cellar. And that way I can tell if any bottles have left the wine cellar without my permission. And I was proudly telling this to one of my engineering friends, and he said, there's a bug. And I said, what do you mean there's a bug? And he says, well, you could go into the wine cellar and drink the wine and leave the bottle. So now we have to put sensors in the cork, and as long as we're going to do that, we might as well sample the esters to see how well the wine is doing, and so before you open the bottle, you interrogate the cork, and if that's the bottle that got up to 80 degrees one day, you give that to somebody who doesn't know the difference. But in all seriousness, we will see these sensor networks populating the internet along with a broad range of Internet of Things, appliances around the house, entertainment equipment, things in the office, things in the car, and things that we carry on our person. So I'm going to flip over to, this is the last bit of prepared material, and then we can have a bit of Q&A. In 1998, my colleagues at the Jet Propulsion Laboratory and I began thinking about how we could improve the networking capability for manned and robotic space exploration. Up until that time, almost all the missions had controlled the spacecraft by point-to-point radio links. And we were thinking about Mars and what had been going on there since 1976, when the Viking landers landed. Since that time, in 1997 in particular, the Pathfinder, little small robot, landed successfully, and communications was done directly from the robot to Earth. But there were 4 orbiting satellites around the planet Mars, and we were thinking, well, why didn't we arrange for a network design that would allow the orbiters and things that are on the surface to communicate locally without having to go back and forth to Earth, so that you could actually run a more complex robotic environment on researching Mars using a network very much like Internet. And we thought we could use the TCP/IP protocols because they seem to work on Earth okay, so they ought to work on Mars. And they would, and they do. The problem is that they don't work, it doesn't work, the TCP/IP protocol, between Earth and Mars or between pairwise and planets because they're so far apart. So when we're closest together, Earth and Mars are 35 million miles apart. At the speed of light, it's 3.5 minutes to propagate a radio signal one way, and of course twice that to come back. And when we're farthest apart in our orbits, it's 235 million miles. That's 20 minutes one way, 40 minutes round trip. The TCP/IP protocols were not designed with 40-minute round trip times in mind for flow control and everything else. And then there's this other problem called celestial motion. The planets are rotating, and we haven't figured out how to stop that. So the problem is that if something's on the surface and the planet rotates, eventually you can't talk to it until it comes back around again. Satellites have the same problem. So we noted that there was a lot of delay and disruption in the space environment, and we needed to adapt new protocols to accommodate that. Now, we've got a lot of equipment on Mars now. We have 4 orbiters that are in operation. We had the Phoenix lander in May, which is no longer operating up in the North Pole. We have the 2 rovers, one of which has stopped operating, the other is still functioning. And just recently, the Mars Science Lander arrived on August 5th. All of them are running the prototypes of the standard delay, or the to-be standardized delay and disruption-tolerant networking protocols. So where we are at this point is that we've designed a new suite of protocols for interplanetary communication. They are on board the space station. The prototypes are on board the equipment on Mars. We have them on board a spacecraft called Epoxy, which is rendezvoused with 2 comets in the last 5 years. We have initiated standardization practices at the Consultative Committee on Space Data Systems as part of the United Nations, so all the spacefaring nations can adopt these protocols as standards, which means that over time, as new missions are launched, we will be able to outfit the spacecraft with standard communication protocols so they'll all be able to communicate with each other. And when a scientific mission is done, the spacecraft can become part of a backbone. So we can grow an interplanetary backbone to support communications for manned and robotic communications over a period of decades. Now, the story doesn't end there, though, because the Defense Advanced Research Projects Agency, which funded the original ARPANET, funded the Internet, funded the interplanetary architecture and testing of the protocols terrestrially, has just funded a study to design a spacecraft to get to the nearest star in 100 years. That nearest star is Alpha Centauri. It's 4.4 light years away. With current propulsion systems, it would take 65,000 years to get to Alpha Centauri, which is just a little long for an ARPA project. So one of the problems is a propulsion system that will get you up to 20% the speed of light. This is another really interesting research problem. It's probably an ion-based engine. It might be a fusion-based engine, but whatever it is, it's got to get up to at least 20% the speed of light at the 50-year mark. And oh, by the way, we also have to slow down, because if we don't, we'll fly through Alpha Centauri and we get one photograph, and it's very expensive picture. So we need to be able to slow down again and get into orbit somewhere. That leads to the other question, which is navigation. And think about it. You're a light year away from Earth, and it's time for a mid-course correction. It's going to take a light year for, it's going to take a year to propagate a radio signal to say something about that mid-course correction, and another year or more to get a signal back to see how we're doing. Did the burn succeed or not? This suggests that we're going to have autonomous navigation. I worried about it for a bit, but the astronomers tell me we have a fairly good idea of the proper motion of stars that are in the near, 10 light year range, in which case we should be able to do autonomous navigation. That leaves the other problem, which is communication. The question is, how do I generate a signal that I can detect from 4 light years away? And one possibility that we've been thinking about is femtosecond lasers. This is taking a laser pulse and compressing it down to 10 to the minus 15 seconds, which allows us to take a 100-watt power source and produce an extremely high pulse, high-powered pulse, which should be detectable. But keep in mind, if it's a laser, for example, the beam spread when you go 4 light years is going to be about the size of the solar system. So now you know why I need the interplanetary backbone, because I need to build a synthetic aperture receiver that will collect the signal coming from the femtosecond laser out at Alpha Centauri. There's more to be said, but I don't have time, and I want to give you a chance to ask some questions too. But I thank you for letting me take up this much of your time, and I'm absolutely looking forward to hear what you have to say. So thank you again, and let's get on with the Q&A.